The universe is vast and mysterious, it's filled with incredible objects. Stars are some of the most important. They are the building blocks of galaxies. They provide light and heat. Stars create the conditions for planets to form. Without stars, life as we know it would not exist. Stars have fascinated humanity for millennia. Ancient civilizations told myths about them. They used stars for navigation. Today we study stars with powerful telescopes. We're trying to unravel their secrets. Stars are not just beautiful points of light, they are dynamic and ever-changing. Stars have a life cycle. They are born, they live, and they die. Their life and death have profound effects on the universe around them. Understanding stars helps us understand our place in the cosmos. It connects us to the grand story of the universe. Have you ever wondered where stars come from? These celestial bodies that light up our night sky have a fascinating origin story. How do these brilliant objects come into being? What processes are involved in their creation? Stars are born in giant clouds of gas and dust known as nebulae. These vast regions of space are the cradles of star formation. These clouds, called nebulae, are not just random collections of particles, they are the birthplaces of stars, where the magic of creation happens. Nebulae are scattered throughout galaxies, each one a potential nursery for new stars. They are found in every corner of the universe. They might look like beautiful paintings with their vibrant colors and intricate patterns, but these stunning visuals are just the beginning of the story. These nebulae are stellar nurseries where new stars are born. The process is both complex and awe-inspiring. They are the birthplaces of stars, where the raw materials of the universe come together to create something new. Within these clouds, gravity is at work. It pulls everything together, initiating the process of star formation. Over vast periods, the gas and dust in a nebula begin to clump together. This is the first step in the birth of a star. These clumps get bigger and bigger as more material is drawn in by gravity. The process is slow but relentless. As they grow, their gravitational pull strengthens, drawing in even more gas and dust. This creates a feedback loop that accelerates the process. This process of clumping and collapsing is the first step in star formation. It's a delicate balance of forces that leads to the creation of a new star. The journey from a diffuse cloud of gas to a shining star is a long one. It involves many stages and takes millions of years to complete. It takes millions of years for a star to form. The process is slow but incredibly fascinating as each stage brings the star closer to its final form. But the process is fascinating. Each step is a testament to the incredible forces at work in the universe. It's a testament to the power of gravity and the beauty of the cosmos. The birth of a star is a reminder of the wonders of the universe and the intricate processes that govern it. Gravity plays a crucial role in star formation. It is the invisible hand that orchestrates the birth of stars, guiding the cosmic dance of gas and dust. It acts like a cosmic sculptor, meticulously shaping and molding the raw materials of the universe. From the very beginning, gravity determines the destiny of stars, pulling together the elements needed for their creation. As more and more material gets pulled into the center of a collapsing nebula, it heats up. This process is driven by the relentless force of gravity, which compresses the gas and dust. This clump of gas and dust is now called a protostar. It represents the earliest stage of a star's life cycle. It is not yet a true star. At this stage, the protostar is still gathering mass and energy, but it's on its way. The protostar is in a constant state of evolution, gradually transforming into a fully fledged star. The protostar continues to grow, accumulating more and more material from the surrounding nebula. It pulls in more material from the surrounding nebula, increasing its mass and energy. As the protostar gains mass, its core becomes denser and hotter. The gravitational forces at play cause the core to compress further. The pressure and temperature at the center increase dramatically. This intense heat is a result of the gravitational energy being converted into thermal energy. This intense heat is generated by the gravitational energy of the collapsing material. The protostar's core becomes a furnace, radiating heat outward. The protostar is now a hot ball of gas, glowing with the energy it has accumulated. It's radiating energy into space, a beacon of light in the vast darkness of the cosmos. But it's still not a star. Despite its brilliance, the protostar has not yet reached the critical stage of nuclear fusion. For that to happen, a much more powerful force needs to come into play. This force is the ignition of nuclear fusion, the process that will transform the protostar into a true star, capable of sustaining itself for billions of years. Section 4. Igniting the fire, the birth of a star. In the vast expanse of the universe, amidst the cosmic nebulae and star-forming regions, a remarkable process unfolds. This is the story of how stars, the brilliant beacons of our night sky, come into existence. Deep within the core of a protostar, something amazing is about to happen. A protostar forms from the gravitational collapse of a dense molecular cloud. As the cloud contracts, it heats up, and the core becomes increasingly dense and hot. The temperature and pressure reach a critical point. This is a pivotal moment in the life of a star. The core's temperature soars to millions of degrees, and the pressure becomes immense, setting the stage for a transformative event. This triggers a process called nuclear fusion. Nuclear fusion is the heart of a star's energy production. It is the process where lighter atomic nuclei combine to form heavier nuclei, releasing vast amounts of energy in the process. This is the moment a star is truly born. The ignition of nuclear fusion marks the birth of a star, a moment of cosmic significance. The star begins to shine, radiating light and heat into the surrounding space. Nuclear fusion is the process of combining lighter atomic nuclei into heavier ones. In the core of a star, hydrogen atoms, the simplest and most abundant element in the universe, fuse together to form helium. In the core of a star, hydrogen atoms fuse to form helium. This fusion process releases an enormous amount of energy, which is the source of a star's brilliance and longevity. This releases an enormous amount of energy. The energy produced by nuclear fusion radiates outward, making the star shine brightly. This energy is what we see as the light of the stars in the night sky. This energy is what makes a star shine. The light and heat emitted by the star travel across the vast distances of space, reaching planets, moons, and even our own eyes on Earth. The outward pressure from nuclear fusion balances the inward pull of gravity. The protostar becomes stable. This delicate balance ensures that the star remains stable and continues to shine for millions or even billions of years. It has now reached the main sequence. The main sequence is a phase in a star's life where it spends the majority of its existence steadily burning hydrogen in its core. This is the longest stage in a star's life. During this time, the star maintains a stable output of energy, providing light and warmth to any surrounding celestial bodies. Our Sun is a main sequence star. It has been in this stable phase for about 4.6 billion years, providing the energy necessary for life on Earth. It has been shining for billions of years. The Sun's energy output has been a constant source of light and heat, driving the climate and weather patterns on our planet. It will continue to do so for billions more. The Sun is expected to remain in the main sequence phase for another 5 billion years, continuing to support life on Earth. But not all stars are created equal. Stars come in a variety of sizes, colors, and lifespans. Some are massive and burn brightly but live short lives, while others are smaller and burn more slowly, lasting for billions of years. Section 5. A universe of stars. Variety in the cosmos. Stars come in different sizes, colors, and temperatures. Some are small and faint, others are massive and incredibly bright. The color of a star can tell us a lot about it. Red stars are relatively cool, blue stars are extremely hot. Our Sun is a yellow star. It has a surface temperature of about 10,000 degrees Fahrenheit. The mass of a star determines its lifespan. Massive stars burn through their fuel quickly. They live short, brilliant lives. Smaller stars like our Sun are much more efficient. They can live for billions of years. The variety of stars in the universe is astounding. Each star has its own story to tell. Studying these differences helps us understand the evolution of galaxies and the universe itself. Section 6. Our Sun and Beyond. Examples of stellar diversity. Our Sun is a fairly average star. It's a yellow dwarf star. It's about halfway through its main sequence lifespan. But there are stars much larger and more impressive than our Sun. Betelgeuse is a red supergiant star in the constellation Orion. It's about 700 times larger than our Sun. If Betelgeuse were in our solar system, it would extend beyond the orbit of Mars. On the other end of the spectrum are white dwarfs. These are the remnants of stars like our Sun. They are incredibly dense. A teaspoonful of white dwarf material would weigh several tons. Neutron stars are even more extreme. They are the collapsed cores of massive stars. They are only a few miles across, but they are so dense that a teaspoonful would weigh billions of tons. Section 7. The twilight years, stellar aging and red giants. As stars age, they begin to run out of hydrogen fuel in their cores. This causes changes in their structure and appearance. For stars like our Sun, this process leads to the red giant phase. When a star runs low on hydrogen, its core contracts and heats up. This causes the outer layers to expand and cool. The star swells up and becomes a red giant. Red giants are much larger and cooler than their main sequence counterparts. They have a reddish appearance. During this phase, stars can become unstable. They may pulsate or even shed their outer layers into space. The red giant phase is a critical transition period in a star's life. It marks the beginning of the end. But what happens next depends on the mass of the star.